Hey, welcome to NASA Launchpads. I'm your host, Vince Whitfield. Hey, you want to see something really cool? Check this out. Yep, that's a paperclip. And it's not sinking. But wait, how is that possible? The paperclip's more dense than water. And we know that if the density of an object is greater than the density of water, the object will sink, right? So why is the paperclip floating? This demo works because of a property known as surface tension. And surface tension is also responsible for some pretty cool tricks with liquids in space. Here's Canadian Space Agency astronaut Bob Thirsk to explain what exactly is surface tension.
Molecules at the surface of a liquid experience unbalanced molecular forces. Since they are on the boundary, the molecules are attracted from inside, but not from the outside. This causes the surface to behave like a stretched elastic membrane. Life on the Earth is dominated by gravity. Think of the things you use every day. You ride in a car, you eat with a spoon, you sit in a chair, you drink out of a cup. All of these things inherently depend on gravity. But up here in orbit, the effects of gravity seem to disappear. With gravity out of the picture, other forces start to dominate our daily work. One such force that becomes very important here in orbit is surface tension. Here in space, surface tension is critically important, even for something as simple as getting a drink of water. If I poured out this drink of water on the Earth, gravity would smush it flat. But here in orbit, it floats in midair. It makes a perfect sphere.
So, you can see that there's a lot more going on with surface tension than just sinking or floating. And it's easier to see those perfect spheres of water in space. But you can see spheres starting to form if you have a leaky faucet and quick eyes, or a high-speed camera. The mass of the water hanging from the faucet slowly builds until the force becomes too strong for the surface tension to bind it to the faucet. And at that point, the drop falls and forms a sphere. In fact, even if the water is coming out of the faucet in a stream rather than drops, with enough distance to fall, the stream will actually break up into drops and then spheres. Spheres, spheres, spheres. What's surface tension's fascination with the globe shape? Well, let's send it back up to Bob for the answer.
Surface tension arises because of tiny forces acting between the individual molecules of water. These intermolecular forces are like tiny springs connecting all the H2O molecules. If this sphere of water is slightly stretched in one direction, the tiny springs pull it back to its original shape. The water always tries to be in a sphere because this way the little springs are all stretched the same amount. None have to work harder than another. To share the work evenly, the water takes the shape of the least surface area, which for a freely floating object is a sphere.
Wonder why water forms a sphere? Molecules in liquid water are mutually attracted, but can slip and slide past each other. That's how liquid water can take on the shape of the container it's poured into, such as a drinking glass. But water molecules at the surface aren't much attracted to gas molecules whizzing in the air above them. Their main attraction is towards other water molecules in the glass. The result is a tense, tight surface, almost like a thin, rubbery skin on the water. Some insects can walk across this skin on the surface of a pond. This surface tension is the key to the shape of water spilled on the ISS. As a parcel of water free falls on the ISS, surface tension pulls the water into a sphere. How come? Since a parcel is a free-floating blob, it has one smooth surface exposed on all sides. All molecules on the surface tend to be tugged towards the center of the drop with equal tension by their fellow molecules. And so, the blob of water pulls into a compact sphere, the most efficient shape in nature, with the smallest possible surface area. Oh, we're almost out of time. Want to learn the trick with a floating paperclip? Just putting the paperclip on the water would lead to a sunken clip. But try this. Rip a piece of tissue paper, put that on the water first, and then put the paperclip on top of it. Then, carefully poke the tissue paper, not the paperclip, until the tissue sinks. With a little practice, the paperclip will be left on top of the water. Now, we know it's not floating in terms of density, but rather it's being held up by the surface tension. That's how some water bugs can walk on water too. There's more to learn about surface tension, but that's all the time we have for now. Until next time, I'm Vince Whitfield. Thanks for watching NASA Launchpad.